Okay, how are you? Two are missing. Who else is missing? Yonghyun is missing. Anyway. Okay, example, the number 2. This is kind of the last, well, not the last, at least FORM. This is kind of understandable. The second example for 2 random still variables. Then I'm going to go through for simply for 20 random variable. Then I have to start assign the group project. Then you can really solve still second problem and the third problem. Okay. This is in my lecture note. If you look at the example 4.2, you will see that this is a cantilever beam. And this is a cross section of the beam. So it's really rectangular, the cross sections. And the length, this length is L is 100 inches. This is using the gravitational unit, English unit, and some are metrics. Some example problems use metrics. So I think it's a good idea to use both units to get familiar. And for this one, for the cross-sectional, I'm going to make it a little bit large. This is a fixed, length is a fixed, it's not a random variable. But you can make a random variable. What does it mean? Length could be like the mean is 100 inches and standard deviation is something like 2 inches, okay? Then the L will be the random variable. So here is loading. This is a px and py. So px, py assigned the random, the variable. That means you have to assign the statistical property. So in this case, this is 500 pound and 100 pound. So what does it mean? Mean and standard deviation. So we're going to use all normal. If it's not normal, really problem for multidimensional. So if it's a log normal, not bad. Because if you take a natural log of the random variable, then that quantity follow the normal distribution, then you can handle nicely. So otherwise, a couple techniques I'm going to introduce next week is mean value FORM and Monte Carlo method is another approach. But if you could iterate 100 times to get the answer using like normal distribution case, Monte Carlo, you might have to try out something like 1,000,000 times. But you're not going to do it by hand, of course. using the computer, then you can solve that. And the PY is 1,000 pound and 100 pound than normal. So two random variables, px and py. And this width is w. This w is 2 inches. Of course, you can assign w as a random variable. So any quantity which has the variation, you can assign the statistical property for those quantities. And that one and this is this beam height. So this is T is equal to 4 inches. And idea is, so the G function idea is, for the G function is, this is, let's say maximum deflection. So assigned as 3 inches, maximum deflection. You can assign this value as a random variable. But to solve in 2D, okay, 2D, just assign the 2 variable as a random, which happen to be loading in this case, okay? It's very clear. And minus actual deflection. Okay, so that's a GX. So, and of course, the actual deflection, if you use a basic, the strength of material or solid mechanics 1, I don't know what you call. I don't think we have such a basic the mechanics here, but that has to go down to undergraduate. Some of you are not mechanical or civil or naval architecture, so it will be a little bit tough. But so this book nicely giving you the equation or formula to compute this, but most of you, as I see you, should be able to compute or generate the equation for deflection. Moment area method, all different kind of method you can use it. But one of the the manual is very useful. I checked my shelf. I didn't bring it from US, but there is a book called Steel Construction. Name is like a Steel Construction. I think it's manual. From AI, as I recall, AISC. Check it out maybe in the library. There are a whole bunch of the equations set to compute the stresses, deformation, for all different quantity, the basic geometries and all that. This is like American Institute of Steel Construction. This is the one book I bought when I first started working at industry, this is one book, late 60s. Even Yunseok said, wow, 60s. Your mom and dad didn't get married yet, maybe. So, check this out. It's very useful. Still, they have updated versions on that. All the equations to compute the deflections and all that, you can find in there. And so this is, of course, this is a tip deflection. The equation on that is 4L cubed E with T square root of Py divided by T square Px divided by W square. Just to present the formula, take as a formula in this class, okay? Then actual, when I say deflection, this is a tip deflection, tip. This is a tip. Okay. So the force is applied laterally, then it's also the loading is applied vertically. Okay. So final could be final could be is not in that direction. The vector summation. This guy could move in that direction. This guy could be in that direction. So vector sum has to be get. So the tip is the bottom. Or you can just say this as resultant deflection. It's simple solid mechanics. Okay, problem is probability of failure. Probability of failure is, how can you define in this problem? Of course, it's Gx is less than equal to 0. Okay, so it's a matter of the reliability calculation or probability of failure calculation. So you expect a very small value, right? And or you can compute the R, which is 1 minus PF. Okay. So let's do the calculation. So if you look at it like this, if I just write, I'm going to rewrite here, PF is equal the probability such that Gx less than equal to 0 is equal G, this is what you need, Gx, you can cast into the Gu function, okay? Make a transformation into U space. So then you can use a standard. No, I'm not going to say any word. Anyway, I'm glad you woke up and Joan is still in sleep, I'm pretty sure. I stopped by, he wasn't there. Anyway. So in the transformation procedure is identical as we have done Monday. In the U space. So in the U space, what you do is Px is equal to Ux sigma Px plus Uy is a sigma Py. Does it ring the bell? X into the U space, and Py is equal to Uy sigma Py plus, I'm sorry, this is correct. This is one term, next term is simply this. This is really coming from the U, x is equal to mu x, ux, what am I doing? Today is only Wednesday. This is Px, right? Correct? Transformation, change into the standard normal distribution function, sigma y. This is from the uy is equal to py minus mu y, and the sigma. I'm going to use the y rather than as a subscript py. That's simpler. So over here, I can use rather than this, I can simply say x for simplicity, as we have done Monday. Seems like this. No problem. Okay. So this is really nothing to confuse. This is same as really this, but to simplify. This is same as mu py. Just use one subscript rather than double subscript. Then transformation, if you do that, that's what the x I can do is px and py. Two random variable, px, py. All others happen to be the constant value. So this is equal to, which is right here. So mu x and ux sigma x mu y. Oops. What am I doing here? X plus, right? Mu y plus uy sigma y. Now we are in the U space, U domain. Then I can rewrite gx into the U domain. Convert into the U domain. then we can handle nicely using standard normal distribution function. If you do this, this u is equal to d0. d0 happen to be constant, is 3 inches. Then 4 LQ EWT. This is a prep work. And you have two terms. Mu x plus ux sigma x over w square, which is the width of the beam cross section, mu y plus uy sigma y over, check it out whether any part is wrong. This is a square and this is a square. It's all good. So now you're on business now. Now you're on business. Then you can start the iteration. And that's one equation you must prepare. What's the second equation? You have to compute the gradient, right? Gradient of g, because if this is your g is equal to 0, you have to get the gradient of that guy. So we have to compute that. So we're gonna put up the u, which is equal to del gu over del ux del gu del uy, evaluate at the u naught. We use a superscript naught, first to try our vector. Evaluate at the u naught. So this component, you have expression for g in u space, then you have to take a partial derivative. You can do that. But it's messy. So if you look at my lecture note, there is a long UG. I'm not going to bother to write here. 4 L Q E W T. There. You take a look at your those write-up is all there. Of course, you can do by hand. I'm not denying you cannot do by hand. There's a lot of the terms, lots of parameters you have to stick them in and compute. Then automation for iteration is a must. And of course, I want you to complete this after you set up the MATLAB program, and this you should be able to do within 2 hours, I guarantee, because calculation is not that much, and also all the equation on this is spelled out. But I want you to verify his result So then you have to report back. So let's do some couple of iteration. Then I'll assign. Then you can do it maybe this afternoon. Two hours investment this afternoon to complete the 4 iterations. This is not a group assignment, but everybody should do that. So then Friday, I want you to, just a couple of people, 2 people can come out. Or prepare in PPT, then you can just show your procedures to compute the second problem. Okay? Would you do that? I'm not sure whom I'm going to point. Could it be Yunseok? Could it be anybody? Maybe Il-young. Okay, iteration number 1. Iteration number 1. What's the first to do? Yongyan, you were top in the midterm. What's the first parameter to compute? U naught. Okay, what's a U naught? You assume, right? Again, I'm not demanding you must start from the origin, but if you don't have any particular reason, origin starting 0, 0 is a very good point. 0, 0 is UX and UY, which is showing UX, UY is all there. And then what's the next one? Now this is a set, trier vector, U naught. Then next, you can compute the GU naught, right? Where is the GU? Here is the GU. For that equation set for this problem, all the variables you know, then you can compute that. I want you to, of course, compute, and if you do that, I said the book said GU naught is 0.6707. That's enough. 4 places on the decimal point. And check it out. I computed, my answer is slightly different from the DO's calculation. DO's graduate students. Okay? DO's, that's why solution manual is all made by graduate students. And you have to really check because lots of errors. But approach is all good. And what's the next parameter to compute? This one, right? Gradient. Now you have to compute the gradient. So gradient is delta G in the trier vector. How many components? two component. So this is delta G U, delta Ux, delta Gu, delta Ui, at U naught. If you do is minus 0.3728 minus 0.0466, only carry 4 places, that's enough. Equation set is there already. So, okay, then you can, what's the next one? What's the next? You have to get the norm, right? To compute the A vector, which is a unit vector of the gradient. Then you take a negative A to change the direction matching with the U vector, unit U vector. So which is U naught, which is a square root of 0.3728 square plus minus 0.0466 square. So now you are ready to compute the A vector. So in my calculation, it's over here. So next is for A vector. A vector is delta Gu at naught, and delta Gu is there. You have this here, you have that up there. You can compute that. So how many components? This is a vector xy component. So you compute this is minus 0.9923 minus 0.1240. Unit vector. So this is a vector, and you have up here, this is A, but now this guy is coming here, which is the U vector. If you take the norm, that's a scalar length, then beta happen to be equal to the norm of U. So now this U vector, U is pointing this direction, but this is opposite. So we're going to make this guy negative, just to review, and it's going to point opposite direction. Then this is equal to what? U over, which is a unit vector, pointing in that direction, same direction. So this is equal to that. So that's where we are heading here. So now A naught vector, you got that. Okay, so A naught is done, and the beta naught is equal to what? U naught absolute, which happen to be equal to 0. This is a one iteration. Then you can do the second iteration, but here, once you got the beta, then we have to update the U vector from U naught to the U1. So keep update, right? then check out the acceptable criteria. So then you stop if its difference is equal to or less than the very small quantity you can assign. So which is minus A naught, beta naught, plus delta G U naught, God bless you, delta G U naught. Yeah, all quantities here. This is here, this is there, this is here, or whole thing is here. A naught is here. So everything is all there, right? If you do that, A naught you got here. So if you do that, then the value happened to be 1.7722, 0.2215. As a practice, when you put it out, the output, you can nicely format all these values. So you can make a table. That's what the Professor Du did. Make a table, and to really see how it converges into the final U star point. Okay? So this afternoon or tomorrow, you should do this calculation. Then iteration number 2, very same. No differences. Iteration number 2. But still this is, it's not a trivial solution, but it has lots of limitations built around it to make the procedure really works well. And same thing, iteration number 2. So from the U naught, you compute the first iteration value. So first iteration value was down there, is a 2 component. This is a value. First, you have to compute first at least 2 or 3, then you can check it out, the acceptable criteria. Then delta G, now first iteration value, minus 0.3894, minus 0.3678. What's the next value? Delta G U1. This is simply square root of this guy's square plus that guy's square. Because this is simply norm. Norm is 0.3916. Next one is A1, which is identical situation, which is equal to minus 0.9956 minus 0.0939. So beta 1 is equal to U1, because this is simply length from 0 to intended ux, which is u star, which is equal to u1 in this case, which is equal to 1 point. Norm, you can get, you can compute from here square root of this guy square plus that guy square. So next one is kind of the final. Now you can compute the u2, which is equal to a1 beta 1 plus u1 So if you compute that, this is two component, of course, 1.7375.1639. Keep update. You can keep update and compare. And the full iteration So iterate, you have to keep iteration, at least the second iteration. Now it's a third iteration, even fourth iteration, try out even fifth iteration. Apply the stop criteria, then you can compute that by comparing. So by looking at this, U value in this is the second iterations, right? This is second iteration, and third iteration and fourth iteration, coming out like 1.7367.1638. Fourth iteration comes very close each other. This is second iteration. This is pretty close. Even the second, this is the second iteration, U2 comes very close. Even so, not many iterations you can do this. Once you got that, you can compute the beta, which is equal to U4. So if you do, this happen to be 1.744. So that's about the final. So beta here is at the first iteration you got 1.7859, and if you 759, next one is 1.7453, and the last, the third 0, 1, 2, 3. So third iteration is 1.744, very close to the end. So you can compute that. So now is enough to compute the probability of the failure? That's enough? What's the PF? So if you compute the phi minus 1.744, so now you look at the table or MATLAB, if you punch it, you can get the result, which is equal to 0.04 0.05. So which is equal to 4.05 times 10 to the minus 2. Is it good, acceptable for your structural reliability calculation? Is it good, acceptable in reality? In your judgment, what can you say? 저기, 윤석. 10 to the minus 2. You invested 1조. Not acceptable. What's acceptable range for probability of the failure? At least less than or equal to 10 to the minus 4th power. It's, if a small sensor was to blow up, no problem, you can replace it. Go out to the store, pay 10,000, then you can get the new one. For $10, you get the new. For this, you have to pay 1조. So it's not acceptable. Minimum, usual minimum, I did the first week of the lecture, 10 to the minus 4. 10 to the minus 4. You can say 1 multiply 10 to the minus 4, at least. And for different structure, you have a slightly different criteria. Minimum is 10 to the minus 4. So when you, as a group, to generate the project, keep that in mind. You may not know at the beginning, but once you write the program, then you can quickly compute and check. So keep the design in mind. I don't want to give you analysis as a term project. Term project, you have to design to survive. That's what you have to keep in your heart. Not the simply analysis. Don't look for the one number. Design has lots of options. Who control? You control, not I control. 0.04, okay. So reliability is, I always write this, or I can say phi beta. That's what we have done, right? So if you do that, reliability is concerned 0.9595 in this lecture. So these two example is a pretty nice example, but this is again, as I mentioned, don't do as a group. Individually, I want you to program out. Or if you feel, oh, I'm not really familiar with the MATLAB, then talk each other. That's fine, okay? Talk each other and learn the MATLAB, because you need a MATLAB at least as a tool to compute. So then you can learn at this time how to write, to make your life simple. Now, professors has a problem. Why? Including myself. We all have a 연구실, right? Then students are so fast. If I do sit down program, may take a long time, but for students, I had a fantastic students in US. Gosh, he's so bright. Overnight, spending a few hours, he can do so much, so well. So then I have a kind of the bad behavior. I always giving, dog, would you compute this? Would you compute that? Would you compute that? But Higyu is my student. Would you compute this? Would you do this? Would you do that? Then he ran away to nonsense. He's gone, you know. I miss him so much. But he's gone. Okay, problem number 3. Nothing much to explain. You have, this is a simply supported beam with 6 different loading, vertical loading. And its time is up. And dimension is all random variable. And loading is all random variable. So assign the 20 random variable. Large problem. You have to think all different things. And the problem number 3, I want you to do as a group. Okay, as a group. Don't turn in this Friday, no. We have to do the discussion next week. Even this Friday we can discuss it, then you can start working on what I want you to work on, using this as a model to start, to begin with. Okay? Then, as a group, I want you to generate some sort of your own design problem. In other words, what does it mean? It's not just to compute the PF, oh, this is 10 to the minus 2, or I have to change the parameter, you know, oh, then this is another PF. No, that's not what I want. I want for this particular project, my target, my goal for PF is 5 multiplied by 10 to the minus 6. Then I want you to conduct a little bit sensitivity study, how the result can be changed, how the design parameter can be changed. So use your own way of thinking, and the 3 of you can discuss nicely, get a very nice design problem set. Then next week, I want you, each group, I want you to present your design project thought that we'll all discuss together here. Then that project I want to pursue to the end of the semester. If I feel that's a very meaningful term project, then I'll stop and no exam. If you do so, then exam to check it out. To check it out. That's what we're gonna do, okay? That's what we're gonna do. So that's then of course I'm gonna give you, of course, lectures on the Monte Carlo. Monte Carlo is very straightforward. And another topic is mean value, first order, the reliability method. I'm gonna give you that's very easy. Easy means there is a trap. You can just get into the trap, then never be able to get out. You can get into the local minimum. Then as you look around, it's a wall, you can't get out. Answer is wrong, something like that. Okay, so Friday, we'll see you and get this problem number 2 results. Don't spend more than 2 hours. It's not going to take more than 2 hours. Okay? All right, I'll see you.